Okay, all right, let's get started. Okay, so from last time, what we've been talking about is power electronics, right? So last time we started talking about power electronics. But basically, if you look at the electronic circuit, then there's few components it's made out of. Right? So we talked about electronics. Then one of our base components is a diode. Then we have the switch, right? So this diode model gives you one-way current flow. Then we care about switches. So this is ideal switch. For us, this is a bipolar transistor. And the idea is a bipolar transistor this is a current control. So it depends on how much current you're putting into the base. So we put a lot of current into the base, then the transistor is on. If there's no current to the base, then the current is off. So here we have this switch is off. So you have an open circuit, right? So the switch is off. Yep, we have open. Then we have this. This is roughly at the saturation region. Then the switch is on. Right, so here we have a closed circuit if it's at saturation. Right? So this is our switch, right? So this is our switch. So if you look at the switch, if you look at the bipolar transistor, the good thing is that this is a fairly robust device. It handles high voltage, high power, this kind of thing. But then what is a drawback of this device? That requires a current to be on and requires a fairly large current. Because remember from last time we computed that a power transistor cannot operate in the linear region. So it's either no current at the base or a large current, large enough such that you saturate the transistor. Right? But then whenever you're on, you're required to push this current at the gate. Sorry, you're required to push this current at the base. And then this is and it's not a small current. So it's not very efficient to have to be pushing current to be on. Okay, so we rather have some device that can turn on and off without continuously putting in a current during the state. Okay, so this can lead to high losses because I have to I have to drive it with some current. So today we're going to look at something called a Thyristor or a silicon control rectifier. Really, what this does is try to allow us to also electronically control the circuit, but without, let's say, always putting current. Okay, so we want putting some current for a little bit, but then not when it's on. Sorry, we want to avoid the situation when the switch is on, that we always put in current, which leads to high loss. Okay, so Thyristor is or you see things like SCR, silicon control rectifiers. This is a device that allows you to turn on without keeping the current going all the time. Okay, without keeping the current going all the time. So let's look at what this thing does. So if you look at it, it's basically a diode with a little sort of tab at the end, right? So if we have a diode, we have this, we have SCR, well, we have this control dial. Right? So this stands for a gate control. This is called a gate, or you can think of this is where you're seeing the control signal. And the reason we have this kind of device, is the following: is to basically have a controllable AC to DC converter. There's a reason there's to have a controllable AC to DC converter. And the idea is the following: if you look at AC to DC converter, so let's say we have a source. Right? Let's say this is AC source. Then I put in a diode. Then I put this into a load. And then you measure the, let's say, the voltage here. So let's call this VS. Let's call this VL. So this is VS. Let's say some AC sine wave. TVS. Then what is VL? What kind of output do I get as a load if I'm putting a diode?
You get only the positive wave.
Right, you get only the first half of the waveform, right? So this is, I only get this part of the waveform. Right, so right? So this waveform give you some average voltage. Let's say this waveform give you some average voltage. But then what if I want to change this average voltage? Right, so here I do get a DC waveform. There is no negative voltage here, so it is DC, it's all positive. So this will give you some this will give you some average voltage. But then this average voltage is completely determined by the peak voltage or the RMS voltage of the source, right? And this is not always ideal. Again, you can think of different situations. Let's say you have a wall outlet, right? Then whether you're charging your phone, charging your computer, or charging your electric vehicle, the load may require very different, right? The load may require very different voltages, right? Your phone definitely requires a different charging voltage than, say, your electric vehicle. Right? But then if you have a diode, then you have, the waveform is set. You get the positive part. And out of the wall, we get, AC 110 volt voltage. Okay? So there's not much control to do there. So let's say I want to reduce the voltage here. What can I do? Let's say if I just put in a diode, the DC voltage is too high. I'm getting too much current, too much voltage. Can I modulate this somehow? Can I have a finer control?
Can you use one or more diodes than just one?
No, you cannot. No, that will not give you more control. No. A diode fundamentally is not controllable enough. Suppose I only want half the voltage. Potentiometer is a meter, right? Suppose I want a, let's think about it, right? So let's say I want only half of the wave. I don't want the full wave. See, variable resistor is also bad, right? Because I don't want to touch the load, right? I want something, see, I don't want to draw more, I don't want to burn power that way. I don't want a variable resistor. I don't want to burn power that way, right? So one simple way to do this, is actually to add a switch, right? So let's add in a switch. And we have a switch, we can time the switch to only give off us, let's say part of the waveform. Okay? Right? So if I want, let's say I have a switch signal that's, let me add a switch with a diode. Let's do this. Let's make sure it's DC, right? So I'm going to add a switch with a diode. And then I'm going to time-wise my switch as off, on, this kind of thing. Then if you look at your load, it'll be 0 here because the switch is not on. Then it will be something like this. Then be 0, then you have another positive part, something like this, right? So the switch will give you more control of the wave, right? So here you can pick out, only a portion, portion of the waveform that you want. You can control the, let's say, the average output voltage that way. You can control the output voltage this way. Right. Any question about this switch? Okay, so this is our switch, right? We have a switch, and this is gives a lot of controllability. But then, as we said, the bad thing about using a switch in power, using a power transistor, a bipolar power transistor switch, as you're losing, you're always putting in a current whenever the switch is on. So this is not very efficient, right? You have some loss whenever the switch is on. And if you're on a lot of time, then a lot of time, you're burning, right? You're burning some more power. You are consuming a lot of, you're wasting power. Okay? With this controllability. So the idea is to have something that can give you a part of the waveform without having a switch. Okay, without having a switch. Right? That's basically what SCR does. So what the SCR will do? What SCR will do is the following. If you look at the circuit with SCR, it's basically a combination of a diode with a very crude switch. And the way crude switch does is the following. It will let only a part of the waveforms through. So we'll let part of the waveform through, and then we'll drop to 0. Then we'll let part of the waveform through, we'll drop to 0. So the difference between the SCR, let's say, and the switch is very flexible. You can turn on and off as often as you want. Where for SCR, we're basically selecting when the SCR should be on, and then we'll turn off once the current or the voltage drops to 0 again. Okay, so that's the operation of SCR. So it's a way to flexibly, you can think of as a controllable diode, right? And our control is we don't need all the flexibility of a switch. So we can avoid some of the current losses, some of the loss from having a switch by just triggering on it once. And so let's take a deeper look at the SCR, what SCR tries to do. So again, SCR, as a reminder, is this is a diode. Again, this is, you draw a diode picture, except here you have a gate. Okay. So gate is where you put in a current pulse. And the gate is set up in the following condition. Okay. Gate is set up in the following condition. As what you want to do is, if we have SCR, when it's negative, when the voltage from the anode to cathode is negative, we want to act like a diode. So if you look at the voltage and the current, if it's negative, we still want this to be very small. We want this to be essentially a diode. So this is similar to a diode operation here. When it's positive, what happens is the voltage will rise, and up to a point, this will start to turn on again. Then this device will turn on. Okay, so up to some voltage, this is a open So this is open circuit. There should be no current flow. But then once you hit a triggering voltage, then suddenly the switch is on, and then now becomes a conductor, now becomes a closed switch, becomes a wire. So this is a triggering voltage. So operationally, what you do is when you have the gate, you're trying to hit the gate. You're trying to hit the gate such that once the voltage is large enough, you're putting a current pulse into the gate, and then this diode becomes a wire. Okay, this diode as a wire. So our goal is for closing this, for making this a closed switch, to say we need two things to close it, right? We need the first condition we need is this voltage is positive, right? So I need a positive voltage. So it's a diode. It's a diode plus it's a controllable diode. So this needs to be on. Then two, we apply a triggering current. To close it, right? This becomes a closed switch. A neat thing is this triggering current is only applied once. Okay? So once you apply the triggering current, it's on, and will turn off only when the voltage crosses zero again. Okay, so once you only apply a triggering pulse, it's not a continuous current into the gate. Unlike a switch, unlike a bipolar in the continuous current, here you need a current pulse. Okay?
So triggering current or triggering voltage?
Triggering current. Triggering current. We're going to trigger with a current.
So then why in the graph do you call it the triggering voltage?
This is based on the way you set when the is triggered is to measure the voltage. So it'll become clear next when we're talking about the conditions. But let me be a little bit clear as let me see. Let me call this a turn on voltage. Let me call this turn on voltage. And you turn on whenever you get a current pulse. Okay, so we'll inject a current pulse, and then this becomes a closed switch. That's a good point. Okay, so that's the operation. That's when we want to. Okay, so that's when we want to. So that's when we want to turn on. Basically, it's diode, so start acting like a diode. Whereas diode starts conducting immediately, once the voltage is larger than zero. This will only conduct once we hit it with some triggering current. And once we hit it with some triggering current. Any other questions about this?
Yeah, I actually had a question.
Yeah, sure.
Could you explain the graph? Like it's kind of like just kind of explain like the motion of that line. Kind of confused about it.
Right. So let me talk about the opening condition. I'll come back to this graph.
Okay.
Yeah. Good. Okay. So let's talk about So let's talk about this is a closing condition. So the opening condition. Right now, let's take a simple open condition. As you say that, right? So this. Right, so this becomes an open switch. We'll have a pretty simple condition as whenever this thing hits zero again. Okay, so we're gonna think of this as right. This will become open when the voltage across it becomes 0, become less than 0, less or equal to 0. So right now we will not have a, so there are more specific way to do it, but right now we'll just say it's what this whole thing turns off when the switch VAK, when the voltage is less than 0. So let me explain this graph and what I mean by these two things. Let's take a closer look to what I mean by these things. So again, think of our source voltage, right? So let's think of again as our source voltage. This voltage, okay, so this is our source. It's time t. Okay. So now I'm going to put in this through a thyristor or SCR, silicon control rectifier. And what this silicon control rectifier, I think how this thing works is, okay. So what I want is I don't want this entire positive part of the waveform to show up when it's a dial. Okay, I only want, say, a portion of it to show up. And the way we determine to parameterize what does a portion of the voltage mean, let's look at the following number. Okay. So if you plot this in terms of the angle and not time, what naturally turns out to be this is pi. Okay. And let's say we only want this to turn on after angle alpha. Okay. So we want SCR to be on after voltage has angle alpha. Okay. For example, we can say alpha is 30 degrees or pi over 4. Right? So we want to wait a little bit until this thing turns on. Oh, SCR. So SCR is silicon control rectifier. Yes. Right, so SCR. So SCR is so silicon because it's a semiconductor device. It's controlled. We can determine what the angle is. Rectifier means it's like a diode, only gives you the positive part of it. Right? So that's where the name comes from. So this is SCR. Okay, so I only want part of it. Okay, I only want part of it. So what I want as the load is I want this, right? So up to alpha, I don't want any voltage, right? I don't want alpha to have any voltage. After alpha, this goes on, reaches the maximum, and comes down to the angle pi, then it's off. Okay. Any questions so far with this? What we want from the device? So this is what we want the device to do, what we want the device to do. Okay. So now let's look at our VI curve. Let's look at the voltage to current curve, right? What does the VI curve looks like? This is a voltage. Let's say this is a curve. Okay. So as the source voltage starts to rise, right? For a while, until some voltage, you're off. Okay, you're getting nothing, right? We're not letting the current pass. This still acts like a open circuit. Okay? Like an open circuit. We're not letting the current pass. Once a voltage is bigger than this, right? So by this time, at the angle alpha, at this angle alpha, we apply a pulse. Okay? We apply a pulse. This pulse is applied to this gate. Right? So this is control pulse. We apply to the gate. And once you apply a current pulse to the gate, what this device acts like is suddenly now it's a wire. It's a closed switch, acts like a wire. So then what does the voltage across the device do? Well, since it's a wire, it really does not, there's not a voltage drop, right? Ideally, there's very small voltage drop. So thus now suddenly this voltage goes back to being very small, and the current can increase with a very small voltage drop. Right. So once it's on, so this sort of curvy picture is showing that you need to get to a certain point, right? You need to get you're only the switch is only turned on, or the SCR is only turned on once you get past the angle alpha. After that, you look pretty much like a diode or like a wire. And then the voltage drop across SCR is small. Okay? So the voltage drop is large up until the triggering angle alpha, then becomes small because now it looks like a diode. And for a voltage that's positive, we'll let the voltage pass. Does this make that? Okay.
Yeah, that makes a lot of sense.
Okay.
Thank you.
Thank
Okay,
you.
so yes. So this is the operation, right? So this is the alpha is basically we get to pick alpha. Okay, so the control is we as designers to get to pick alpha. So I only want a little bit of the waveform. I can pick alpha very close to pi. If I want, let's say, most of the waveform, I can pick alpha close to there. And again, this instead of using, so you could realize this using a bipolar transistor switch. But again, this has a benefit of you only apply one pulse. Once it's on, it's off. It's like a diode. You don't need to continuously apply a base current for this to be on. So this is a very important technology for power transistors. Okay, this is very important for power transistors. Right? So for something like a VRSI circuit or embedded system, then normally you don't need this device. You can just have a switch, right? You can just toggle the switch. The thing is, for power applications, the gate one is we use bipolar, right? So the gate current, the base current, is not can be significant. The loss can be significant, right? So that's why you don't want to do everything with transistors. Whereas for VSI or integrated circuits, you can do everything with transistors. You don't need this. All right. Okay, so this is, yeah, go ahead.
Do you apply current to the gate every period, or is it just once?
You want to apply it every time. So there's a driver. There's basically a small controller attached to it that drives this.
Cool, thanks.
Okay, right. So this is a very important device. So this SCR is a very important device. You'll see this device many times in this class. So a lot of conversion is basically dealing with some equations with respect to this device, right? So the way this works is we change alpha to get the average voltage we want. Then we have some filtering elements, to make this wave look more DC, right? But the way we get the average correct is by changing alpha. This is by changing alpha.
Quick question.
Yeah, go ahead.
So you said we just varies the location of the alpha, right?
Right. Yeah.
So basically, if if usually the voltage maximum is 120, and then if you want 50, you just varies the alpha until the max is 50, right?
Yeah.
Okay, thank you.
Yeah. So so it's not that, right? So because this is a sinusoid, so it's not you want half the voltage alpha. So it's not a linear relationship, but we'll get to that relationship. But the idea is correct. Alpha is your control variable. Alpha is our control parameter. So this is the way. Yeah.
Sorry.
Yeah.
So I'm confused about the turn on voltage because you said we need to send a current pulse in order to turn on the gate, but that it also gets tripped by the turn on voltage. And so is the turn on voltage the voltage drop across the SCR while it's building up? And if so, then wouldn't that automatically hit a point as the quote unquote current keeps going through it, and therefore it's going to drop more voltage until a certain point?
No. So no. So the idea is, so let's back up, right? So whenever you compute alpha, you're computing based on when you want to be on, and the way we're going to do computation is we say, okay, this SCR should turn on, at this voltage value, which translates to this alpha, right? Which translates to alpha. So that's a voltage. That's a voltage we want SCR to turn on. Then what your control circuit will do is to, at that voltage, send a triggering pulse, say you're on. Okay. So we're controlling when to send the triggering pulse. We'll send it once the waveform hits that angle. But the way we'll compute what alpha is basically looking at the voltage. Let's say, okay, we want it to turn on at this voltage. So your logic will be, I want to turn on at this voltage. Then your controller will compute an alpha, and at that voltage, will send a control pulse for it to turn on.
Thank you.
Yeah. So for us, if you look at this as a device, you can think of, okay, I can program a turn on voltage for this thing to be on. But no, right? So the actual thing is, at this angle, you trigger it. But often, when we're doing calculations, it's easier to think of this will turn on at this voltage, or this will turn on at this angle. But the way you actually physically control it is you don't program an angle into it. You basically send a current pulse to turn it on. Okay, all right. So the Thyristor, so there's a lot of advantages. That's why we like to use this, or SCR. This is the terminology is used very interchangeably. There's many advantages. As one, this is actually, we can do this with high voltage and current ratings. Okay, so it is again a very robust device. So it's more robust than a switch, because it's definitely more limited than a switch. Okay, so more limited than a switch. Right? Switch are designed to operate at the tens, even for power transistors, tens or hundreds kilohertz, where this thing operates once an AC cycle. Right? So it's sort of it's more limited, but you can make it much more robust. This is really cheap as well. It's cheaper than a power transistor. This is lower loss, as we said. It only needs to be only need to apply one single pulse per turn on, so it's lower loss. And the nice thing is, this sort of have a natural. The technical word is commutation. Commutation means that you stop conducting. Natural commutation when right. So the nice thing is, we'll turn off automatically when the voltage drop back down to 0 again. But once you hit this angle pi, voltage drop to 0, this thing will turn off. It'll become a diode again. Okay, so you don't need another pulse to turn it off necessarily. There's a natural turn off point, and this is called a commutation. And this, as circuit designers, a lot of time this is very desirable as a turn off. The disadvantage with this thing is, often in your circuit, you need to be careful the current actually goes back to 0. Okay, so you need to be careful that we need to be careful that the voltage drop actually falls below 0, so it turns off. If you're relying on this sort of natural commutation to turn your circuit off, then often the bug that happens is that it's actually not getting to 0 when you want it to get to 0. If you have a switch, you have a very explicit control of on and off with a switch. But if you're relying on this for 0 voltage switching, then you need to make sure in circuit design the voltage is actually 0. voltage actually gets back to 0 for this kind of switch. Right. Okay, so this is our advantage and disadvantage of a SCR. So in the first lab, for example, we'll be looking at SCR. We'll do a bunch of simulations to see what happens. Okay, any questions? So later in this class, we'll be going through all the equations associated with SCR. There are some of them that are important for us to know in this class. But the thing to remember, again, often when you're interview somewhere, I will ask you, why do you use SCR? Why not just a bipolar switch? Right? Why not just a bipolar transistor? It's important to remember why we're using SCR.
So if it's an AC circuit, how is it possible that the voltage wouldn't go back to 0?
It's not always that simple. For example, you may have an AC circuit, but you may have an offset somewhere. So the voltage goes back to 0, but maybe not where you think it's going back to 0. You may often have what's so-called a polyphase circuit, where it's not one single AC phase, but it's many phases together, and you want to rectify this one. Then 0 voltage switching requires timing between different phases, and that's you need to be very careful. So we won't show up in this class. For us, the AC wave will always be nice. When we actually design it, especially when you guys so-called a polyphase circuit, then you need to worry about exactly when they're crossing 0.
So what do you mean by the polyphase circuit? Like there's like a bunch of AC graphs.
All right, so yeah, so this is getting way beyond the scope of this class, but normally, right, so what I mean is later in this class, we'll see actually all the AC system, we mostly see a 3-phase. Okay, we just have a naturally 3-phase circuit. But then often you want more phases. The idea is, the more phase you have, it's easier to basically cancel out the variations in each phase. It makes your performance better when you have more than one phase. But then we have more than one phase, you need to time them pretty well. There's also a timing issue. And then it's important to do that timing. And when you rely on this kind of 0 voltage switch when it's off, when this hits 0, you need to be careful when things hit 0. So there's, this is beyond this. We won't go into that circuit design. But if you go on to take more power electronic classes, or even if you take something like integrated circuit, when you have voltage regulation, you'll face this kind of issue. You'll face this kind of timing issue here. Okay, so this is just something to remember. So we won't see it, even for 3-phase, we'll mostly assume there, it's a balanced 3-phase. But when you go to practice, when you design this kind of things, then this kind of commutation becomes very, very important. How does it turn off? Right? This becomes more important. So interested in this, please take I advise you take the power electronic classes that we have in the 400 level. We'll go into a lot more detail about this. Right. So for us, a Thyristor is just a nice device that think of it depends on the angle alpha, gives a way to control the angle alpha. Right, so stepping back a little bit, right? So right now we have 3 devices. We have a diode, we have a switch, which is just really a bipolar transistor. And we have SCR. Okay, so out of this, 3 devices, we're going to build power converters. And for us, there's 4 types of power converters, right? Because there could be AC DC, right? This could be AC to DC, AC to AC, DC to AC, DC to DC. Okay, so we're going to see how we build all 4 types using these 3 components, using our 3 basic components. So let's just do a very brief overview of what they're used for and why do we have 4 types of them. So AC to DC is what we talked about, and this is perhaps the most sort of common ones we see is you have a sinusoid coming here. And at the output, you have a DC voltage. Output, you have a DC voltage. So this has applications basically for us as the most common ones is anything to do with electronics. Whenever you're charging anything, you have AC to DC. And then batteries, if we want to think about storage, this requires converting AC to DC. So this is our converter. DC to AC means that I have a DC wave input, and then I want an AC wave output. And please think of application for this that you see, let's say around your home. When you want to convert DC to AC voltage.
Like a solar panel gives you DC, so you want to convert it to AC.
Right, good, right? So this is solar, batteries, these are all give you DC, and
What a
about to DC generators are rare. DC generators are rare. Mostly as this sort of renewable devices or batteries that converts DC. Generators are very rare. Right, so this is, we can think of solar batteries, or when we talk about backup power supplies, UPS, this is where you need DC to AC. So one thing that's weird is AC to AC, right? AC to AC. Why we want AC to AC?
Does it change the phase?
Right, good. One is changing the phase, as this is a phase shifter.
Is this also like relating to those like AC amplifier?
AC, but you don't see them a lot in power applications. You do see those, but not so much in, say, the grid applications. Yes, but they're definitely used. Yes, they're definitely used. Right, so this is, right, so AC to AC, right? So there is an AC to AC converter, that's called a transformer. Right, we can step up, step down ACs using a transformer. But here we're talking about electronic ones. So what this does is one is shifting the phase. What else may you want to shift with the AC waveform? Voltage is easy, right? So I can shift the voltage or the voltage amplitude just using a transformer, which is a sort of more developed technology. I don't need a converter, right? Frequency is another thing you want to shift. So a transformer will not shift frequency for you. It seems impossible almost to shift frequency with a transformer, but we do want to. Sometimes we want to shift frequency. There's when we want to shift frequency. What appliance in your home, for example, will want AC power, but maybe not at 60 hertz? So these are mostly, if you look at your home, these are mostly motor drives. For example, your washing machine. Right? So your washer and dryer may not want to go at 60 hertz, or they may not want to go at a multiple of 60 hertz. And you may have variable speed drives that just doesn't go at a multiple of 60 hertz. They need to change the frequency. So these are basically for motors that can run at variable speeds. You want to shift the frequency. And most time, the way we build AC to AC is to actually have a back-to-back converter. That looks like this. You chain AC to AC, AC to DC, and DC to AC converter. And that turns out to be the way most of the time how we build an AC to AC converter. So we don't need to change the frequency or the phase. A lot of times you just use a transformer. That works. But if you want, you need fancy control at the end of the day, then you won't do an AC to AC converter. Then we go to DC to DC, right? So the last converter we have is DC to DC. Then this is basically, let's say you want, output at one level, you want to output at another level. So this is often used when we have electronics. So we have this a lot. We have this is called a buck converter or DC to DC converter. And there are things that require multiple voltage levels, and you have this kind of buck converter. So you see this a lot, for example, in some applications, more often than in, let's say, something like a ship or airplane, where you have multiple voltage levels and you need to convert a DC voltage to multiple levels. So all of these are used. All of these are used. And then a good example that sort of puts everything together is you can think of an electric vehicle. So electric vehicle is actually where you find all this converter, or most of these converters. You find most of these converters in one device or one vehicle. Okay, so you look at electric vehicle from a circuit or power perspective, it's basically a bunch of converters connect to each other. That's one way you can interpret. One way you can interpret electric vehicle, right? So, easily when we have, for example, when you look at battery charging, the power flow is from the grid through the AC DC converter into the battery. So this will use the AC to DC converter. And depending on how full your battery is, you definitely need to change the average voltage the battery sees. Okay, you have a lot of control circuit on your battery interfacing with AC to DC converter. Right? So this is important to have control of this converter. Yes, SCR is important to have here. We have driving as driving as a battery going to the AC motor. Right? So you pull power this way. We need a DC to AC converter because I need to drive. Right? So I need something that's variable frequency, but to drive a motor, I still need AC power. So the motor actually, when you build an electric vehicle, the motor itself has not changed very much. A lot of times it's the same motor you will find, in other vehicles, or it's a motor that has undergone a little bit of design, but not much. Where a lot of innovation is actually in the electronics, in the converters. So a lot of times you spend more effort designing the DC to AC converter, maybe not as much time with the motor, because induction motors are very well developed technologies. So that's driving. We have braking, right? As pulling these things this way. You're braking, you want to dump power from the DC side to the AC side, which then goes into the battery. Actually, that may be a little bit more careful with this. Braking is, I have a generator. You want to be careful that you're routing power the correct way into the battery. And then last thing we have is the vehicle to grid, meaning you pull the power from the battery into the grid. Right? Maybe the grid needs power. Maybe you have a blackout somewhere. You want to use a vehicle as your vehicle as a storage device. So you can pull power out of the battery into the grid. But today, this is not yet used today. This is not very common today. This is not very used. This is not used very much today. Can you guess why? This is natural application. The vehicle being to grid has been talked about for the last at least 10, 15 years, but still not very common or not used at all today. You think of any reason why? Right, or you as a driver, let's say you buy a electric vehicle, why would you, maybe not like having it to the grid, pulling power to the grid? So what does cost mean here? It has to do with cost, but specifically cost to what?
You the consumer. Go.
Sorry.
I just have a quick question on the
Sure,
grid.
go ahead.
Like, what does the vehicle to the grid mean?
Oh, you use a vehicle as a battery. My grid
Oh.
needs some power. I use there's a big battery sitting in the vehicle. I want to use it as a battery.
Right now, there's no way to monitor what that is, so you're going to be paying to continually charge your car and not getting reimbursed for putting it back in the grid.
No, we can monitor what it is. We can measure the power coming out of your home. That's where these smart meters can measure that. So you have a good idea of how much power you're pulling out of it. It's related to that. It's not because we cannot measure the power coming out of the battery. That we can measure. Yes, we can measure the power. But the question is, right, how do you compensate for this power? Because if you're supplying power to the grid, really what happens is you're degrading your battery, right? So as for all batteries, this thing runs down. A battery after a year of operation will not have as much capacity as a new battery. This is no. But when you're driving the vehicle and you're charging it, well, you have to use power from the battery. But then once you want to supply power to the grid, then the question is just, how does the grid pay you? How do you get compensated? How do I measure the right? So there's a benefit to the grid, but there's also a cost, the degradation cost to your battery. It's unclear, how do I measure this degradation cost to your battery? And then as a driver of the vehicle, is you don't want to degrade your battery too much such that you have to swap out your battery. Battery costs a lot of money. It's the most expensive part of the electric vehicle. But today we still haven't figured out this quite yet. We still haven't figured this quite yet. We don't have a very good idea of compensating for the degradation of the battery. That is a lot harder to measure. This is the actual power pulled out of the battery. That's easy to measure, but how the battery actually degrades is a interesting and more difficult question. So there's many companies and startups and academics working in this area, thinking about if you have this battery whose primary usage is not for the grid, but maybe can help the grid out, and how do you price this correctly is an interesting question that many people are thinking about. Okay, so this is just something to keep at back in mind, right? So let's take our break. Then we'll talk about each of these converters. We'll start with AC to DC, then go through all these converters, get the actual equations for all these converters. Okay. All right, so let's take a break to 3:36. Then we'll look at AC to DC converter. Okay, all right, let's get started again. So during the break, there's a question of, how much difference does vehicle to grid make, right? Is it an important application or not from the grid perspective? So it's not clear how important this will be. It's not clear from economic perspective. And also it's not clear, in general, if it is something that we should mandate an electric vehicle to do. But still, we can do a back of the envelope, very ballpark calculation. I see, it may not be, it could make a difference, So as our calculation, let's do the following. So remember Texas a few months ago had this big blackout, right? So that's right. Since this is the most recent blackout, there's another joke that probably most of all calculations in the next few years will be based on this blackout. But let's do this calculation. So this let's call it. So this blackout was really an imbalance of supply and demand. So there's more demand than supply. So that's why we need to do a rolling blackout. So this, let's say we have about 10 gigawatt, excess demand for 24 hours. Okay, so I'm making these numbers up on the spot. I think they're the correct for the order of magnitude. I think this are more the magnitude correct. Okay, so let's say this is 10 times, right, 10 gigawatts times 24 hours. This is 240 gigawatt hour. I need this much energy. So let's see, how much energy we have in electric vehicles. Okay, so from what Google tells me is Texas has about 0.2 million vehicles. Okay, I have no idea whether this, right? So that's at Google, this is what it says. Now, how big do you think a battery is, right? So let's do this exercise. So we want a order of magnitude estimate of how large a electric vehicle's battery is. Any guesses how large that is? Folks who have right, so Tesla is a special case. Tesla is very, very large. Most, I don't think we're going to replace all by Tesla. So Tesla is around, can get to 100 kilowatt hour, depending how it is, how big it is. But let's say we have, not all 22 million are Teslas. So let's pick a number. Let's say each has, on average, 10 kilowatt hour, okay, of storage. Right, they may not all be full. They may not all be, different state of charge. But let's say 10 kilowatt hour available charge. Let's multiply this together. So I have 22 million, 10 times 10 to the 3. So you get about 220 gigawatt hour. Right? So not too bad, not too bad. So it's close to the 240 gigawatt hour we needed to the supply the demand, right? So if they're all electric vehicles and on average they have 10 kilowatt hours, then you come relatively close to supplying this power to the grid. Okay. So this is of course way too simplistic of a calculation. It's way too simplistic of a calculation, but this is ballpark calculation tells you it's not useless, right? So it's not trivial, right? So they come out, to be very close to each other. So this tells you it's not trivial to the vehicle to grid, right? But still, all the vehicles, being electric in Texas gave you about this much, but still it's not insignificant, right? This could save you from most of the blackout if this really worked. Okay? So this is why it tells you it's maybe a viable application. Really is the key is working the engineering part out, right? If I have 22 million vehicles on the grid and they all want to supply power to each other, now you give the grid operator a heart attack. Right? But maybe doable, but I don't know how the grid operator will handle it right now. And also, how do you compensate for this? Right? What if my battery dies after doing this? All of that needs to be worked out. But it's not hopeless. It's not hopeless. Right? So there is a need to figure this out. And again, there's a lot of opportunity in this area. Right? As if I buy an electric vehicle, instead of just adding a 10 kilowatt load onto the grid, right? How do you help the grid? And then if you own the electric vehicle, how do you get the most bang for your buck, right, of helping the grid? From the grid perspective, what kind of economic program do you design? Right? Do you incentivize them in a special way? Do you, are there, for example, people are talking about using AI technology for this? So, yeah, there's 22 million of them. So I don't want to solve an optimization problem with 22 million variables. Right? So can I use AI to do this? Does learning give you something reasonable? All that is open question, but it's something, for you guys to think about, right? Especially given that the next few years will look like there's to be a huge electric vehicle push, right? From all levels of government, from the manufacturers, from the state legislature, all that is coming. Then really, this is not a solved engineering problem. Often the engineering part is solved. You're waiting for policy. This, in some cases, the policy is running in front of the engineering problem, right? As engineers, we don't know what happens when, let's say, 22 million of them are electric. I don't know what happened to the grid. I don't know how we will charge this, but they're coming. So when policy is, in front of the engineering, running ahead of engineering, there's a lot of opportunity here, right? You're not waiting for a customer base. You're not, waiting for revenue stream. There's a revenue stream already there. Okay? For you guys who want to think about this, this is something to look for opportunities in this space. Go ahead.
So I guess my only confusion with it is how is it really a positive? Because at the end of the day, the person is going to want to take the power back out of the grid to charge the car anyway, right? So like most people hook their car up at night when the drain on the grid's pretty low anyway compared to what it is during the day. So what's the real upside when the person eventually is going to want to take that power back and charge the car?
Oh, timing wise, right? So you look at Texas, you're 10 gigawatts short for those few days. Right now, if you want to add 10 gigawatt of load onto the grid, go for it. So when you need the power is really, really important, right? So all battery does is shifting power around. But Texas was bad at that time because there was no generator. You couldn't turn generator on. The week after the winter storm, Austin hit 75 degrees. So at that time, if you wanted 10 gigawatt of power, sure, the grid can supply it. Right? So really a timing-wise issue. Right? The ability to shift load around in time is quite powerful. Quite powerful. You can talk about from carbon perspective, right? Is this carbon neutral or something like that? But then from a grid reliability perspective, it's very important to be able to shift power around.
So the thoughts to have it more is kind of like an emergency backup plan rather than something that is continuously going back and forth?
No, even have it as continuous going back and forth may be valuable, depending how, let's say, for example, when you look at solar generation in California, it'll be really nice if I can move if I can spread that solar generation around, evenly in the day, rather than concentrating those 5 hours in the afternoon. It'd be really, really nice if I could, move this to be more aligned with the load. Right. So there could be continuous opportunity if you can justify the cost. If we can work away, we have better battery control algorithms, we understand degradation better. We have better batteries. We can align up load with better. Could make a difference. Like this, a small flexibility in time goes a long way in power system operations, actually. Like so, a little bit amount of storage often makes a huge difference in power systems. Yeah, so all this is being think, right? This is really new. Again, our grid is not designed to do this. And really our operation, how we operate the grid, we didn't think about this. But still they're coming. So this is right. So this is perhaps a sort of most exciting time for power engineering in the last, I'll say 40 years or so. Really, you have new devices is coming, and we need to figure out what to do with them. Any other questions on this topic for vehicle storage? So for now, we can only use pump hydro. Yeah, so mostly right now, the largest ones are pump hydro. Yeah, well, right now, the largest one pump hydro. Or pump hydro will dominate power storage. There are niche ones there and here and there, but most are pump hydro. So what pump hydro means is you dig a lake, right? You build a lake, and they have excess power. You pump water up to the reservoir. Need power, you use that as a hydropower station. So that's mostly the power storage we have now. But that requires, there's only few locations you can do that. There's only few locations. And that's pretty much tapped out in a lot of places. Okay, all right, good. Okay, so now let's go back to the technical part. Let's look at our AC to DC converters. And then a interchangeable terminology you see as this is called a rectifier circuit. Okay. So these are used really very interchangeable. AC to DC versus rectifier, they are the same thing. They're pretty much, there's the same thing. And you see, even within one textbook or one paper or one menu, they'll be used interchangeably. So be prepared, right? You'll see both terminologies. Right, so the simplest one we have, so let's start with our diode, right? So this is the simplest rectifier we have. This is called half-wave rectifier for obvious reasons, because you get half the wave. So this is, you get the first part of this wave. The rest is 0 until the start of the next period, because I put a diode in the middle of the circuit. So let's do some calculations with this half wave. For example, what is the average voltage across the wave? Right? So let's say we want to compute the average output of this waveform. Okay? So remember, our formula is the general formula is always R to 2 pi. So this is called VT. To make this larger, V sub T. The load voltage, we're using notation V sub T for terminal voltage. So thus we integrate VT over a period of 2 pi, d omega t, or 2 pi. But since the after pi, this whole thing is 0, so we're really integrating from 0 to pi. Right? From only integrate from 0 to pi, let's say V max sine omega t d omega t. When you integrate this just becomes out to be V max over pi. It's the way the integral works out. And so this is the average voltage of a half wave, right, of a half wave rectifier. Right, so, okay, so all this, we'll give a table for the equations later, but now keep in mind that these are the equations you want to know. Okay, so often a question will becomes, a simple question will be, we put a waveform that has a Vmax of 170 volts into it. What is the average voltage of the half wave rectifier? So we can also change this. What is it in terms of RMS voltage then? Let's say I have a source voltage with certain RMS voltage. Then what is this average voltage? What do I divide by here?
Root 2 times pi.
Root 2 times pi, right? So root 2 times pi. Good. So, right, so this is just the simple half-wave rectifier, goes from 0 to pi. Now, as we said, we want to control this, right? So next, let's look at a controlled half-wave rectifier. So we're going to add this to here. So we're going to now make this SCR, silicon control rectifier. And we're going to take only part of the waveform, take only part of the waveform. So this is a SCR instead of a diode. So let's say, how does this depend? So if you use SCR instead of diode, as when you have a diode, it only turns on right at 0, right when the voltage is positive. Here it turns on at an angle of alpha. So if it turns on at an angle of alpha, so if you look at again the let's not cover this. Right? So let's say what happens when it turns on at the angle of alpha. So the voltage follows a very similar profile as, the current follows a very similar profile as a voltage. So if the voltage turns on here, then if you look at the current will turn on, will follow the same shape after scale by R. So this is the current. All right, so this is, instead of voltage, we talk about the current, but current turns on at the same triggering angle as voltage. Right. So here we have the alpha being turned on, whereas you have beta, then here beta equals to pi, right? We'll turn off at pi, at angle pi. This will turn off at angle pi. So if you compute the average voltage across a load, if you compute the average voltage, then instead of integrating from 0 to 2 pi, we'll integrate from alpha to beta. We'll just integrate from alpha to beta. And this integral, we can work it out. Let's work this integral out. This is average as 1 over 2 pi. So here, take beta equals to pi. Instead of integrating from 0 to pi, we integrate from alpha to pi. V max sine omega t d omega t. So this comes out to be V max over 2 pi 1 plus cosine alpha. So depending on the angle alpha, we get this average voltage. Okay, so let's check if this makes sense, right? We said V average. Let's do a sanity check of this equation. Right, let's do a sanity check, meaning does this line up with our intuition about how alpha should work. So if alpha equal to 0, what happens when we set alpha equal to 0? Right, so we set alpha equal to,
You get V max over pi.
you get V max over pi, right? So this recovers the half wave. Right? It has a half wave rectifier. So we got V max over pi. So this makes sense. Let's say set alpha equals 1/2. Sorry, not 1/2, pi over 2. Or 90 degrees. We get V max over 2 pi, right? We chop off half the wave, so we get half the average voltage. Still makes sense. On the extreme, alpha equals to pi, this gives you V average to 0. Meaning, right, you never turn up. Right? If your triggering angle is pi, then you actually never on. So you get 0 average voltage. Right? So if you plot this graph tells you if you want a certain, again, output voltage, you can go to this graph and pick out an alpha. Right? You can pick an alpha to give you the average voltage you want. That's why control is nice. Right? Control of this SCR is nice. Questions about this?
Can you explain again where when the alpha is pi over 2?
Oh, when
And
the alpha is power 2? Okay, sure. So let's say alpha is power 2. What's cosine of alpha? What's the
0.
cosine of alpha? 0, right? So this is V max over 2 pi. So you get half of the average you would have gotten from the halfway rectifier. Right? So because you only starting after the sine hits its peak. So you got half of the way. You got half of the halfway rectifier.
Then you just average from that half, right?
Yeah, just average. So when you integrate, the alpha is where you start to do this integral. So you're just integrating from that half. Okay.
Okay, thank you.
All right, good. All right, so this is a very this is a smooth trade-off between the triggering angle alpha versus alpha voltage you want. So of course you cannot get more than V max over pi. Right? So the highest average you can get is V max over pi. You let the entire positive part go through. But then you can control how much of that you get by changing this alpha angle. All right. All right. Okay, so let's now look at, so this is average voltage. Of course, we want to look at the root mean square voltage, right? So as before, for all this, we talk about power. Power is the square of the root mean square voltage, right? Not the average voltage. So often the root mean square voltage is more important for us. So let's look at that. Let's look at what the root mean square voltage is for this equation. All right, so if you look at the root mean square voltage of this load, then the calculation is still the same as basically VRMS. This is equal to square root of alpha to 1 over 2 pi. This whole thing to pi V max sine omega t squared d omega t. So this, instead of the average, we're putting a square to compute the root mean square voltage. So this turns out to be, something that's not that easy to compute. So I'm just going to state the result here. This is V max over 2 square root of 1 minus alpha over pi plus sine 2 alpha over 2 pi. So this is what you get by plugging in, by doing the square and integrating everything. Okay. So this is again, as alpha, goes from 0 to pi, this becomes smaller and smaller, right? Becomes smaller and smaller. So if instead of picking an average voltage to pick alpha, you can pick a root mean square voltage, then picking out the alpha you want. Right? So if you want, you can substitute VRMS for the source. We'll square root 2 into this and write everything in terms of the RMS of the source. So any question about root mean square voltage?
Yeah, so we first talked about VRMS for like dealing with AC stuff, but now we're going from AC to DC, but still using VRMS is helpful.
Yes. Yes.
Okay.
Because the power depends on VRMS. Because power is VRMS squared over the load, right? Not V average squared.
Okay.
Right? Because that's sort of right. So what power is, right? Power is V squared over R. But you're squaring the V inside the integral. And you have to integrate that and find the average. So power just depends on VRMS and not the average voltage.
I see. Okay.
Yeah.
Thanks.
Yeah,
So
because
it's-
the actual weed that we see every day is basically VRMS, right?
Yeah, VRMS. Yeah. So almost all for AC, for anything that has a sign, even the after rectification, the V you see is RMS voltage. Is RMS voltage. Because what you really want to do is you want to say V squared over R is power, right? Whatever V gives you that equation, that's the one we want. And turns out RMS voltage works for that power equation. Okay, all right, good. So let's now actually go into power, right? So again, VRMS is important because I want to talk about power in terms of VRMS squared. So power is V RMS squared over R. Okay, so this is for after rectification, you still need to square the root mean square of the voltage, right? The root mean square of voltage relates to power, not the average voltage, not the average voltage. It's the same reason that for AC waveforms, we cannot look at the average. Same thing happens here. Same thing happens here. So this is, of course, IRMS squared over R. This is, so we can square everything, right? This is Vmax squared over 8 pi R, 2 pi minus alpha plus sine 2 alpha. Again, you get this equation by just squaring this. By just squaring this. So for reference, I typed out all the equation here. So this is an important slide to know how to find. We're doing your exam or doing your homework. That's an important slide for equations. And questions about this? Equations?
Yeah, I had a question.
Sure. But
So is that RMS of the voltage that could be used for the controlled half-wave rectifier and the regular half-wave rectifier?
yes, for the regular wave, for the regular one, then you put alpha equals 0.
I see. Okay.
So half wave. This is alpha equals 0. Plugging alpha equals 0, and all the equations work.
Thank you.
Thank you.
Right, so you don't need to derive these equations, right? You won't be asked to derive these equations. You definitely be expected to find these equations, and also very fast. Okay, so yeah, so just be aware of where to search for those equations if you need them on the midterm or the final. Okay. Any questions? Other question about this? All right, so next is full wave, but that is better to do in conjunction with DC to AC. Okay, so let's stop here today. Next time we'll continue with this discussion. We'll finish most of the power electronics stuff. All right, so basically we'll do the full wave rectifier, then we'll do DC to AC, and then we'll do the DC to DC converters. Okay. And this will give you enough information to do your first lab, right? So again, the lab orientation, right? Introduction starts this week. Go to your sections, but the actual lab starts next week. And then as a reminder, homework is out now and dues are still
I had a question about the labs. You said that they're each 2 weeks. Do they take, so like we have our lab time starting next week. Do they take both lab sections to do, or we are in lab for 1 week and then we have a week to do the report?
So it's every other week whenever you're doing the lab, right? So it's every other week. So you're doing one lab, you wait a week, you're waiting between to do the next lab. I think the report is due 1 week after the lab, though.
Correct.
Yeah. So it's not. So you don't have 2 weeks to do the report. You have 1 week to do the report. But there's 2 weeks between each lab.
But we only meet for one section, right? We don't.
Yeah,
meet
you only meet
each week. Okay.
Yeah,
Thank you.
yeah. Okay. All right, so no other questions, then I'll see you on Wednesday.
Hi, Professor. I have one question
Sure, go
regarding the average of the half-wave rectifier.
Mhm.
As you do the conversion,
Mhm.
I think you need to go above a bit. Yeah.
Where did it go? Okay, this one?
Yes, this one. Yeah, I
Okay.
see how you I'm confused, like how you convert the V max to the VS RMS divided by square root 2.
Oh, right. Okay. It should be a multiply, not division, right?
Yeah, it should be.
Yeah, multiply. Yeah, that's a good point. Sorry.
Okay.
Yeah, multiply. That's a good catch. Thanks.
Okay, thank you so much.
Wait, what did you change?
No. So V max square root 2 times the source RMS, right? So it'd be root 2 times
Oh
RMS,
yeah,
not
that
divide.
that,
Yeah.
that was
Yeah.
that was what I thought also. Like I
Yeah,
tried to solve
divided. Yeah, divided where I should multiply. Yeah.
Okay, thank you.
Okay, thank you.
Yeah, thanks for catching those. Yeah, so again, in the future, if you notice something wrong, please let me know. Please let me know.
I was the one who did it wrong, and so I didn't say it.
That's fine. Yeah.